So our next presenter is Nwizu, and he's going to talk to us about novel compounds which combine to the macrophage migration inhibitory factor.
Hi, my name is Chib, and I've had the opportunity to work with Dr. Michael Moser and Justin Navarrete in the development of novel isoxazoline synthesis pathways in order to better bind or antagonize the macrophage migration inhibitory factor, or MIF. And our ultimate goal is to make a molecule that will better bind to these factors with the MIF and help type 1 diabetes patients. So type 1 diabetes is an autoimmune disorder that affects approximately 3 million Americans and is characterized by the quick degradation of the beta cells in the pancreas, which produce insulin. And what happens is the macrophages of your immune system start to attack and destroy the beta cells, and as these cells lyse, they release a signal, a cytokine, which the cytokine actually calls and signals for the migration of macrophages to the aid of the beta cells. But unfortunately, the macrophages don't aid, and they actually attack the beta cells further in the cycle. And so if we can silence the cytokine, we'll be able to stop the macrophages from attacking the beta cells and actually stop the release of the cytokine. And the cytokine that we are looking for is the macrophage migration inhibitory factor, or MIF. And MIF is a pleiotropic cytokine, and in mammalian cells specifically, they actually form a number of transduction pathways. In macrophages, they prevent the p53 dependent apoptosis of the macrophages. And although we don't know how it does this inhibition, we do know that it performs polymerase-like enzymatic activity. And this is simply the switching of certain molecules between isomeric forms. And we know that antagonism, or the binding to a hydrophobic pocket on MIF, actually prevents this enzymatic activity from happening. So what we did was we looked at the molecule ISO1, and it is a highly active antagonist to MIF. And what it is a 3,5 distributed 2-isoxazoline. And this 3,5 distributed 2-isoxazoline is just the added to specify what type of molecule it is. And what the 3 is indicating is that we have a functional group coming out of the 3-carbon position, and the 5 says that we have a functional group coming out of the 5-carbon position. And the 2 is saying that in the second position where it's nitrogen is, we have a double bond. Now what we know to occur is that this phenyl group coming out of the 3rd carbon is able to create a hydrogen bond to the amino acid ASN97 within that hydrophobic pocket. And so current synthesis pathways for ISO1 are good. However, they provide limited control over what can be added to that 3 and that 5-carbon position. Moreover, when we do add we add chemicals to that 5-carbon, we are not able to control what direction it is facing. And then we are not able to add groups to the carbon 4 position at all. And so all of these compounded limit our ability to add groups to the isoxazoline, overall limiting our ability to explore ways of enhancing ISO1 binding to MIF. And so in the focus of our research is to do what others can. We plan on finding ways to add specific groups to the 3, the 5, and the 4 carbons. And when we do add groups to the 5 carbons, we want to be able to control its orientation in space. And the proposed pathways in our research is we want to create a alpha beta unsaturated octane and control the ring closure of it to the 2-isoxazoline. And actually what we do is we are trying to create an intermediate to the isoxazoline reaction, and with that intermediate, we add more steps which allow us to control the creation of the 2-isoxazoline. So when we are creating our octane, what we have to do is first combine acetophenone and benzaldehyde in a base catalyst reaction. And in this case, we use the base catalyst NaOH, which is sodium hydroxide. And this creates an alpha beta unsaturated ketone, or a chalcone. And what we do with this chalcone is we then add hydroxylamine along with pyridine, which is a sweet base, to create this chalconoxine. And with the way that we do this is we are exhibiting a lot of control over the reaction, and we are only creating the intermediate, like I said before. And so we are actually creating 3 products instead of just 1 reactive factor. And these 3 products are the 2-isoxazoline, the synoxine, and the antioxidant. And the only difference between the syn and the antioxidant is the orientation of this hydroxide group. And as you can see in the antioxidant, we have the hydroxide group facing away from the double bond, which is called an alkene. And we have the synoxine, the hydroxide group is facing towards the double bond. And because it's facing towards the double bond, this hydroxide group is able to cyclize and form this 2-isoxazoline. And so in our research, we are trying to control what group we add on to these functional groups, the R1 and R2 position, and that dictates whether we create a synoxine, an antioxidant, or the 2-isoxazoline. And in this, we will be only changing one reagent at a time, and this is just to control what we see and make sure what we see is what we want. And once we create our chalcone, we run it through a nuclear magnetic current analysis, which is an NMR, also called an NMR, and it looks at the hydrogen of the sample that we took. And we look for chemical heat indicating that we made a bond. And here we see that we have made a bond because of the presence of these 2 sulfurs, which just indicate that we have specifically created that double bond between the ethanol and the alcohol. This is the same reaction. We did the same reaction, except we added the group to the ethanol and the For our results, after we create that group, then we create our chalcone. What we do is we run into that hydroxylamine and pyridine reaction and reflux its own 2 hours rather than the original 8 or 6 rate. And we run it through an NMR to look for the presence of the synoxine, the antioxidant, and the isoxazoline. And when we do that, we put it on the tables, and the tables are organized by the sigma p-value, which is basically the effect of the electron withdrawing group of the group that we had, so the effect that has on the overall free energy of our system, which is basically saying the more withdrawing groups we have, the more of a change we actually induce on the central compound. And so this is that same graph, the same table put into a graph form, and we plot it versus with sigma p-value versus the mole ratio, which is that the number of hydrogens in our compound versus the number of hydrogens in all of the products. And this is the same thing for the ethanol substitution. And what we did was we saw trends that occurred in our research. What we saw was that as we increase our sigma p-value, so increase the electron withdrawability of our functional group, we created less and less of the synoxine, so created more and more of the antioxidant. And these 2 actually share an inverse relationship, and we can see that because of the similarities in their both of their trend lines. Moreover, we also see that in our benzaldehyde, we actually create more of the synoxine as we increase our sigma p-value, which is interesting and merits more research. And there's another trend that we see is in the benzaldehyde, this line crossing is saying when we create that automatic crystallization and lose control of the reaction, it is shifted forward 0.1, approximately 0.1 in the benzaldehyde, and shifted back 0.1 in the ethanol. And so we were able to use these trends to further our research and look at other trends. And what we did was we doubled either the electron withdrawing ability or the electron donating ability with our 2 opposites, and we looked to see if we would yield more of the product that we predicted. And so in our graph, in our table, we saw that these methanoxy groups were the most electron donating, while these nitrogens were the most electron withdrawing. And so what we did was we added one methoxy group to the benzaldehyde and a methoxy group to the acetophenone reagent, and we expected to yield approximately 0.6 to 0.68 of the spin-off. But we only produced 0.58, which is more than what we've created so far, but it wasn't as much as we wanted initially. So to conclude, we found out that the addition of certain groups to our acetophenone and benzaldehyde reagents does have an effect on whether or not we are able to control the ring closure. And more specifically, we see that changes to the benzaldehyde actually provide more closure over the ring than changes to the acetophenone. And then when we did do further on our research and look at doubling the amount of groups we had on the reagent, we saw that it did not have a significant effect. It had an effect, but not significant enough to where it would make a difference. And what we actually would like is to have more research done on how the effect of multiple groups on multiple carbon positions. So in our reaction, we only add functional groups to the C4 position of our carbon, and we just want to know if adding groups to the C3, C4, and C5 actually has an effect on creating more or less of the phenomenon. So I would like to thank Alyssa Carlson and Angela Galletti for their help in the lab. There are sometimes when I didn't know what I was doing, and they were an invaluable source of information. I would like to thank Anthony Gaga for his help in editing my paper and guiding me throughout the 60s. I'd like to thank my advisor coordinator, Crystal, who also looked at my paper a few times. And she also gave me advice on how to cite some of the things that I didn't know how to cite. And the Schlesman Family Foundation, they actually gave me the financial means to be at this frontier with the Science Institute, and the Excel Energy Foundation actually gave me the financial means to do the research that I did. And I would like to thank Lori Ball for creating a great program and allowing me to do research because I've never actually done research before. And this was the first time I was able to do it, and I'm so glad that I was given this opportunity. And I will leave this program with more knowledge than I ever had before. Knowledge that you can't just take up from a book. Thank you for listening to my talk, and I would like to open the floor to some questions.
So, I'm not sure if it's quite follows things related, but when patient gets an organ transplant in the body, does the whole trajectory is just monitoring tactics and activities used for that?
Yes, you have the right principle. The MIS are responsible for all types of inflammatory responses, but this wouldn't be used in that because when you have an organ transplant, you're actually putting someone else's organ in you, so the body is actually killing the cells, and those cells aren't releasing the correct MIS that your body creates. So it follows, but I don't think these research specifically can help with that. Yeah.
I noticed when we were showing your graph that the antioxidant production is almost the same for the values in the front.
For what?
In your graph, if you go back to the slide, the antioxidant production is almost the same for all different values, right?
Yeah.
Can you explain that?
So the question was, the antioxidants have no slope, or basically no slope, in both our acetophenone and without high substitution. The exact cause of that is unknown, but we have a few ideas on what is actually causing that. And what is happening is, what we believe is that the strength of the functional group we have does not have a strong enough effect on inducing the creation of a phenol versus a antagonists. And that can be seen in the structure of the octane that we create. The octane that we create has this kind of structure, and they have two double bonds, right? They have a double bond here and a double bond here. And these double bonds are very tight because the electrons are being pulled in more than in the single bond. And because we have these double bonds, we believe that is, and the hydroxide group is all the way up here. We believe that having group on this carbon does not have enough of an effect to change, to strongly dictate whether we form the phenolphene in this case or the antioxidant here.
Can you explain a bigger picture, how all the launches and everything are gonna stop the applications happening?
So the question was the overall picture of what we're doing, how it actually stops the migration of macrophages to the pancreatic cell. And so this octane, the isoxazoline is actually not actively involved in bonding to the macrophage, but we know that the macrophage, if this is the macrophage, it has a pocket in here that is hydrophobic, and in it, this isoxazoline molecule, whatever the case may be, is actually going into this pocket, and it's creating a hydrogen bond to certain amino acids of the hydrophobic pocket. And because it's doing that, for some reason, the change in here is preventing it from performing its job, and it's actually a commerce that I said. And what it does is it controls the conversion of certain molecules between isomeric forms, which is just like the formation of the phenolphene or the antioxidant. Not in that case, but that's what it controls the reaction. Those are the kind of reactions I think. So, sorry. Are there any more questions? Thank you so much.